So for each class, we'll do a recap to recap the critical contents from last week. So first of all, like last week, we first talked about the computer organization. So there are compute memory and I/O. So I think the most important thing is how CPU works to access the process. So actually, when people are saying about process, is about a combination of the program and the related CPU and memory resource, right? So for a program, just like you write a C code and then you will put a C code on the memory. So actually the C code will be first, will be compiled and then to go through the assembler, and then you'll get a lot of instruction there. So actually C codes on the memory, that looks like a sequence of instructions. So CPU reads the first instruction and then do the decoding and execution. So after that, CPU will will fetch another instruction. So CPU does this by automatically increment the program counter. Okay, so there is nothing special here. It's just about to increase the program counter by, for example, by 4, like 32 bits, and then the program counter will jump to the next kind of address. So CPU can fetch another one. So CPU only does the routine works. What I mean with routine works is if there is no like branch condition, like if else, if there is no jumper, like the go to instruction, the CPU will fetch the next instruction and then the next one. Okay. So the next thing to recap is about the Linux kernel part. So Linux kernel is a process manager, consists of a bunch of C and assembly code. And people are usually curious about, like, is Linux kernel a process? I would say no, not that exactly a process. The reason is when we are talking about a user process, like this kind of things, they should have their user address space. Okay. So let's we talk about like the virtual address space part. So we will not go through it today. So kernel runs as part of a user process. So you can see at the right-hand side, usually for each user process, they have their own address space. So including the user part and then the kernel part. Okay, so you can see actually the kernel part is designed for running a kernel process. Okay, so for each user process, when they run the process, actually the lower, for example, 3 GB, they are all allocated for user program. So you can put your user program here, and then you can put your, like, the process can put their process data here. Okay, but for every process, they will leave their top, for example, 1 GB address space for the kernel. So this is the reason I say Linux kernel is not like a process, because they only have their kernel address space. Kernel doesn't have their user address space. Okay, so the reasons, like, each user process has their corresponding kernel part. It is because we say in CPU there is a bit, but actually it's not really only 1 bit, because if you read the OS if you read the OS textbook, they will say there are 7 modes there, or like there are 5 modes there. But I think the most important thing is actually in CPU, there are 2 different modes. One is user mode and the other is kernel mode. So when CPU is in the user mode, CPU can access user process, user program, process data, but CPU will not access the kernel part. Okay. So for example, when there is a patch fault, this kind of things, what I mean patch fault here is when CPU needs to run some OS kernel service. In this case, CPU will switch their mode from user mode to kernel mode. Okay, so switching this mode only involves to switch the bit, for example, from 0 to 1. So it is super fast. So after switching a bit, CPU can access the data or like a function in the kernel address space on the topmost here. Okay, so for example, if this is a patch fault, actually there is a corresponding patch fault handler. So you can think about patch fault handler is just like a function code. Okay, just like a function, it is named by the patch fault handler, and the function is like here. So CPU will start to run the patch fault handler one by one, okay, by its instruction. So this is how kernel works. So the important thing is CPU switch to kernel mode to access OS code, but CPU does not need to switch the context. Okay, so the context here we usually means the user process context. What do I mean CPU doesn't switch the user process is actually CPU only switch to kernel mode and to access the other part of address, but the user address space here, it doesn't change to any other, right? The address space is still the same, stick with the original user process. Okay. So we also use like a toy example, submarine, to let you know what the concept is telling us. Actually, you can think about a submarine is just like CPU running like process A, like here. So when CPU is running user process A, it is in the and the submarine will be on the surface of the water. It means CPU is now in a user mode and running process A. Okay. So when CPU needs to run some OS kernel service, the submarine will dive into the water under the surface. So it means like CPU enters the kernel mode. And in this mode, CPU can run some kernel service. So like file system, scheduler, memory manager, all those kind of things. And the key point is actually for the user address part, this CPU still holds process A. So process A doesn't need to be switched out to other like kernel process. Okay, so this is a key point. We don't really switch the process. We only change the CPU mode. We only change the CPU bits. Okay. So here is more details about how to trigger and request kernel service. So when do CPUs run kernel? Actually, CPU runs a kernel only when some spatial events are triggers. So here are several spatial events. We classify into the hardware events and software events. So for the hardware events, they're like timer interrupts. So for timer interrupts, you can think about usually for each process, they only have a given time slot. So after running out the given time slot, CPU will raise a timer interrupt to say, hey, it is time for you to switch to other process. Okay, because you use too much of time, so you need to let others to run. So this is about timer interrupt. So IO interrupt is quite simple, just like the keyboard and hard disk drive, this kind of peripheral device, when they are going to send the data to CPU, then there is an interrupt occurs. And software generated interrupts usually like traps or exceptions. So you can think about things like system call and like patch fault, those kind of things. They are software generated. Okay. So the same example here, just like here is a user process, and when the submarine is above the water surface, it means the CPU is in the user mode, and when the submarine dives into the water, it means CPU is in the kernel mode. So we use the same example. So when there comes the system call, for example, when you write a program like you are going to read a file or you are going to write a file, then after the library translate, it means CPU needs to do some system call to interact with the hardware device, right? Because when you are saying you are going to read a file and write a file, it means you are going to read something from hardware device. Okay, so usually when there involve some other hardware device, it needs system call. So system call handler, it is a part of the OS service. So CPU needs to enter the kernel mode to run the system call handler. So after finishing system call handler, CPU will switch back to user mode to keep running process A. Okay. And then if process A use up the time slot, for example, it runs too much of time, then CPU will triggers the timer interrupt. So after trigger timer interrupt, CPU will switch to the kernel mode and execute the CPU scheduler. Okay, so CPU scheduler is another kernel service, so CPU should be in the kernel mode to execute it. Okay, so after running the CPU scheduler, usually we will switch out the prior process and then we will run another process. For example, it's process B here, so we change the icon to another submarine to represent, hey, this CPU is going to run another user process. So we call it process B now. Okay, so after running process B, after running a scheduler and then the CPU switch back to user mode, you can see like now process A changed to process B. So CPU now is running process B. So we call this procedure called the context switch. Okay. So from process A to process B, it is context switch. Okay. And then if there comes an IO interrupt, for example, then process B will once again dive into the kernel mode and then CPU can run IO handler. So this is the process about how to trigger and request kernel service. I mean, you guys, if you don't feel like really familiar with this kind of procedure, it doesn't really matter because in the rest of the course, you'll keep facing this kind of example. I'll let you know like there are several kernel service and how it works in the kernel mode. Okay. So let's start for our main course. It's about what is a process. So last time actually we slightly talk about some briefly idea about the process. So today we'll also do the quick recap about what we talked about last week. So first of all, process just like an active program and related resource. So there are several related resources. For example, the processor state, the memory state, the file state, network state. So most of the power resource that this process is required, we'll call them the related resource. Okay. Okay. So because there are so many resources and different resources will have different state, so we need a data structure. We need a kind of a metadata to keep track of those resources. So for each data structure, we call them process descriptor. Okay. So because there are several processes in the system, so there will have several process descriptors. And there is a data structure called task list. Task list is going to chain all the process descriptors together. Okay, so just like the figure on the right-hand side. Okay, so what is process descriptor? So in Linux, process descriptor is just like a function. So just like the task dash structure. So this is a name for the process descriptor in Linux. So it contains all information about this process. So each process has their own process descriptor. So you can take a look at this figure here. So for each text structure inside, there are several fields. So one I think you'll be very familiar with is the process ID. So because of each process shall have their own process ID. So process ID is one of the field breaker in the text structure. So we already talked about this. Just like in Linux, like there are a lot of descriptors. It just means the data structure for maintaining information. Okay. And then in your undergraduate, maybe you still remember there's one word called process control block, right? So process control block or PCB in Linux called it the process descriptor. So they are the same things. So process control block, it is a concept, and process descriptor in Linux, it means the implementation for the process control block. Okay. All right. So there's a quick question: is the difference between process and program? So usually when we say program is when you're writing a C program, when you're writing a C++ program, it's like when you open a kind of a text editor and you put several code on it, and this is called a program. So process, it is a runnable program. So it means process includes some resource, because if you are going to run a program, actually you need CPU, right? And you need memory because you need to put a program on the memory. So when Linux is going to keep track of this kind of information, then those kind of resources are needed. So for process, it means the active program and the related resource. Okay. Okay, so we also talk about state field. So state means like, what is the state of the current process? So actually there are quite a lot. There are 5 states. First of all is the task running. So running means it is runnable. Okay, so runnable means the process is now running, or the process is in the run queue, or usually people call them ready queue. So there is 2 possibilities when the process is in a task running state. It is running now, or it is in the ready queue. Okay. And there's 2 like state for interrupts. So there is a state called task dash interruptible and task dash uninterruptible. So interruptible state means the process is now sleeping, waiting for some conditions. For example, the process is waiting for the I/O completion, because maybe the process needs the data from a storage device, right? But storage device is so slow, so CPU doesn't want to wait for that storage response. So the process should be forced to sleep. So in this case, the state of that process will be marked as the task interruptible. Okay. And there is another very special thing, is called task uninterruptible. So it is also the same. The process is not sleeping now, but it will not wake up by the conditions. What I mean is, actually, it can only be wake up by some special kernel thread. Okay, so usually it is used for the fork process. So when we are going to create a new process, at that time, the new process will be set to the task uninterruptible. Okay, only some kernel thread can wake up this new process. We'll explain this later. So there is also some very kind of spatial state here, but last time we talked about it, so let's skip it now. So, because there is a state, so usually in your textbook, you will see there is a thing called process state diagram. So process state diagram is just like a life cycle for each process. Okay, so let's look at the left-hand side. It is a concept, and the right-hand side, it is the implementation of Linux. So when the process is new, means that the process is just created. In this case, people are saying like we use a fork kind of system code to create a new process. And later on, we will talk about how fork function works like. So after creating the process, actually, the process will be added to the ready queue, or like to add to the run queue. So at this moment, the state of the process will be changed to the task dash running. Okay, so in the ready queue doesn't mean the process is not running. It just means the process is runnable. The process still needs to wait for a CPU, right? Because maybe there are a ton of processes that are in the ready queue, but there are very few CPUs that are available. So the next thing is, if there is a kind of a CPU and it is possible to run the process, and the process will be scheduled and then to be running. So you can see like the ready queue, the process will be picked from the ready queue and then to be run. In this case, the state will not change because it is still the running state. Okay, so both states, there are still tasks running. Okay, so there is a case is, for example, if the process is interrupted by some other process. For example, there are some other process that have higher priority. Then the process will be put back to the ready queue again. Okay, like this, interrupt, put back to the queue. So I think it's here. So if there is a higher priority process, then the process will be put back, and the high priority process will be run now. Okay, so in the running step, sorry, when the process is running by CPU, there are several cases here. So one case is we finish running the process, so it is called terminated. So when it terminated, it means like the CPU should terminate the process, and CPU will release all of the resource allocated to that process. So it is a termination state. And we will talk about how to terminate a process later. So there is another is the I/O or event wait. So one very obvious example is when this process now needs some data from a storage device, and then in this case, CPU will switch the process to the waiting queue. So in the waiting queue, it means like this process is not waiting for the I/O response, waiting for the I/O completion, right? Because the process is waiting for the data in the storage device. Okay. So in this case, you can take a look at this circle. Actually, there are two possible states. One is interruptible and the other is uninterruptible. So it just depends. In most cases, it will be set to the interruptible. It means after the I/O completion, the state will be switched back to the task interrupt. Sorry, the task running. Okay. Oh, there's an animation here. So those are like we talked about last week. So this week, let's start from the process creation. So usually, already know process creation in most of the operating system, we use fork plus execution, right? So fork means we create a child by copying its parents. So it is quite simple. And the design concept behind this fork design is because it is efficient enough. Because when we are going to create a new process, if there is the parent process, we can just directly copy it, and then we can make sure most of things will be correct, right? Because the parent process is not running now. So if we can directly copy most of the resource from the parent process, then we can also make sure the child process, most of the state will be in the correct state. Okay. So there are some fields that will be different. For example, the process ID. So because process ID, each process should have their own process ID. So PID will be different. And like for each process, they have their own patch table. So the patch table will also be different. Okay. And also there are some signals that will be different. Okay. So other than that, most of things, they are same with the parent process. Okay. So the next step is execution. So execution, EXEC, is quite simple. It's just to load a new executable into the address space and run it. So executable, you can think about just like the program after compiling, there is a .exe file, right? So that is an executable. So like the binary, you can run a binary. So the binary is also a kind of executable. Okay. So address space now you can think about just like the memory, just like you put the binary on the memory and system can run them. So executable is just to put the binary file on the memory and just run it. So we will not focus too much on the execute. Let's talk about a little bit more about fork, because there is one issue here. If we are going to copy most of the, I would say like most of the stats data from the parents, it may take a lot of time, right? For example, if this parent process already has a really large memory, for example, 1 GB memory, and if we are going to copy it, it will take a lot of time, right? So in this case, there is a design called copy on write. So copy on write is going to solve the challenge. Just like naively copying a resource from parent is time consuming. So we don't really copy at the time the parent does the fork function. Okay. Then how can the system do the copy? So copy on write works on delaying and preventing copying data until the data is written. So you can think about if most of the data is read-only, then we don't really need to copy the data, right? Because if the data, we only want to read the data, then you copy all data, but they are the same. In this case, why not just share the data, right? So we only copy the data, they are updated. It becomes a new one, okay? So the system will only copy, for example, if the child process is going to update the patch table, is going to write a new data, or if the child process is going to store a new file, because they are new, so we need to write them to a new place. So at that time, we do the real copy function, okay? Unless if the child process only read the data, only read the patch table, and we don't really do the copy, okay? So let me give you a quick example here. So come to think about so let's image like here, the rectangle box here is a physical address. It's just like a DRAM, okay? So we say like we put the binary on a DRAM, right? And on the DRAM, there are several things. The first thing is the patch table. So I think it is quite hard for some if you did not take the undergraduate. So I try to use some example to make you easy to follow it. So you can think about like the virtual address, just like the mail address. Okay, so each house have their own mail address, right? But the mail address is not the mail address is just about, for example, in this country, you know, your mail address is that. But for other country, they don't really understand what is a mail address, right? So there is a more absolute way is the physical address. So physical address just like the latitude and longitude. So you can think about the Chinese for this is like 经纬度, okay? So using this longitude and latitude, you can get the absolute address, okay? And the thing is how to translate the absolute address to the mail address. Then that is called a patch table, okay? So just like if there's a patch table to do the translate from the mail address to the latitude and longitude, then you can people can easily know where is the for example the house. Okay, so after introducing an address, there's another thing is patch, because we talk about a lot about patch from the very first clause. So for patching, you can think about we are going to evenly partition the land, right? For example, if you can think about if there's a country and there is a super large land, then we are going to construct several houses on it. And in this case, how to do the partition? So for the Linux, actually, we will evenly partition the land into the same size. Okay, so you can think about for each 4 kilobyte, we will do a patch here. So just like, for example, you have a super huge land, then you will partition the land into the same size. And that size is called patch size. Okay, so you can think about like this. You can construct a house on the evenly partitioned land. So for example, for each kind of 100 kind of meter square for this kind of things, you will construct a house, and for the next 100 meter square, you will have another house on it. Okay, so each house has their own mail address. That is called each house has their own virtual address, and then also has their physical address, just like using the latitude and longitude. So they are very similar for Linux here. Okay, so in Linux, the LAN is just like the physical memory here. Okay, so for the physical memory, we will partition into the same equal size, the 4 kilobyte patch on it. And for each patch, you can store the data on it. Okay, so patch table is a way to translate from virtual address to physical address. So actually, patch table is also a kind of data. So patch table will also on this LAN, okay, on this physical address. Okay. So, okay. So the thing is like this. So when CPU is going to access the data, for example, it's going to access this patch frame, but CPU doesn't really know where the patch frame is, right? Because CPU only, for example, in this example, CPU only has their mail address, but CPU cannot really understand what is the absolute address is. So CPU will first check the patch table. So inside the patch table, for each entry, there is a mapping between the virtual address and physical address. Okay, so in current CPU, actually, CPU will only get a virtual address. So CPU will ask about where is the physical address. So after CPU getting a physical address, CPU can, in the second step, can directly access the patch located on this physical address. Okay, so this is about like how CPU access the data on it. Then now, if, for example, if process 1 is going to fork another process, so let's say process 2. So actually, after forking a process, at the moment CPU, process 1 forks process 2, the patch table will not be copied. Okay, so patch 1 and patch 2 at the very first moment, they will only share the same patch table. So when patch 2 is going to update the patch table, then the patch table related to patch 1 will be copied and then to modify to patch 2. Okay, so you can think about at the very moment they are all read-only, and when patch 2 is going to write a patch, for example, patch 2 is going to write this patch, then the patch frame will be copied out to the new patch frame, and then the patch table will be updated to point to the new location. Okay, so this is the concept of copy on, right? So the good thing is actually process 2 only need to copy out the patch that they are updated. So the rest of it, for example, for this patch, they are still in the share state. So process 1 and process 2, they still share this patch frame because this patch frame is still not updated by process 2. Okay, so in this case, the process can be forked super fast because in most of the data at the very beginning, they will not be updated. So we'll only do the copy when the data is updated. Okay, so this is just a very kind of tiny example to show you how copy on write works on the patch like perspective. Okay, yep.
We have like, so if we have 2 forks from D1,
Mhm.
we have 2 and 3,
Mhm.
and they are read only, and then write to like D1's page table.
Mhm.
Will 2 and 3 both get their own page frame, or will they be able to share one?
Actually, if there's 2 forks, and then for example, process 2 is going to modify the patch table, then process 2 will get a new patch frame, a new patch table. But for process 3, they will still share with process 1.
It's the parent that changes?
If the parent changes, then the parents will get another new patch out.
Okay, children can still share.
Yep, yep.
一开始它对到的 frame 都是一样的，
嗯
所以直到它有写入或是的要求。
Yep. Yep, correct. Yep. All right, so any questions? Okay, so if there's no question, then let's move on. So this is the roughly concept about the copy and write. So how Linux implement? So Linux actually there is a new function called copy process. Okay, so for copy process, let's talk a little bit more about copy process. So actually, when we are going to create a new process, there are several things that we need to do. First of all is to allocate, sorry, where's my mouse? Okay, so to allocate a new kernel stack, and then process descriptor. So I think I didn't really talk too much about kernel stack last week. We only say, hey, actually there's a thread info. So you can think about like this. When you are going to run a user process, right? And maybe there are some function code. So when you are running a function code and there are some parameters, right? So those parameters, they're usually stored in the user stack, right? So kernel is the same things because when you are running a kernel, like when you are running some operating system functions, there are also the functions. So inside the functions, for example, maybe there are some parameters. So for those parameters, they need a place to store them. So they are all stored in the kernel stack. Okay. So to maintain those information, we need the data structure. So this is called the thread-info. I mean, this is a very simple way to explain it, but actually in a complex way, they are super complex. So let me just skip the kernel stack here. Okay. And another thing is the process descriptor. So because each process have their own process descriptor, so in the very beginning, Linux will allocate a process descriptor for the other process, like the child process. Okay. Okay. So inside the process descriptor, actually there are several fields, right? So there are something that they can be set and they can be copied. So for example, the program counter and the stats, they will all inherit from their parents. And then for the process ID, actually they will be set to the new process ID here. So this is about the process descriptor part, just like the text structure. Or you can think about it's an identification for each process. Okay, so this is the second thing. So third thing here is the stat that we just talked about, the task uninterruptible. So each new process at the very beginning, they will be set to the task uninterruptible. And this is because the process now is still in the initialization state. So we don't want any kind of accident occurs here. So only the kernel thread can wake up this process. Okay, so this is non-interruptible for most of the signals. Okay. Okay, so then we will duplicate parents patch table via copy and write. So the thing is, actually, including a patch table and patch thread, they are shared between the parents and their child. So they will only copy out new patch table and then to copy out new patch frame only when there's some data is updated. So I say like they are copy on right here. Okay. So otherwise, if we follow the original rule, actually we do the fork. Actually, if the process has a lot of patch frame, then we will do a lot of copy process here, and then it will be wasted and will be time consuming. Okay. So actually, there is one very interesting thing is, I think you guys know about there's process and thread, right? So actually, the difference between process and thread in Linux is about how many resources they are shared. Okay. So the thing is in the process, most of the where's my mouse? Okay. For the process, most of the resource, most of the kind of files information, signal handler, address space here, most of things you will finally be duplicated, right? I mean, if there's an update, then we will do the copy on write for the process. So eventually, most of the resource, they will be duplicated out and there will becomes a new one for a new process. Okay, but not for thread, because thread, usually they share most of the information. For example, open files, files and information, signal handlers, and process address space, they are shared between each other. Okay, so this is a difference between process and thread. And there's more details at the next page. So actually, people are saying like thread is just like a lightweight process, and it executes within the same program in a shared memory address space. Okay, so usually when we talk about threads, we are saying like they share open files and patch tables. So the thing is, for each thread, usually they will share a patch table with the process create those thread. Okay, so they will not have their own patch table. So for patch table, actually is each process has their own patch table, but not for thread, because thread share the patch table with their, I would say like with their parent process. Okay. So this is the reason why Linux implements all threads as the standard process. So in Linux, people are saying like, what is a process? Actually, if they have their own text structure, people are saying that that is a process. So for threads, they doesn't have their own text structure. They are shared between each other. Okay. So threads have their own program counter, because program counter means when we are going to run the original code, then we need a program counter to know where is the next kind of instruction. For example, we're going to increment the program counter, right? And then threads have their own register, because they're going to run as like a process, but not really a process. And also a stack, because when you are writing a thread, for example, pthread, this kind of library, when you are writing, actually you are possible to write some function there, and there's parameters. So for each thread, they need their stack to maintain their own like function and parameters here. Okay, and also threads have their own stack. Okay. So in Linux, it doesn't really provide any spatial scheduling or data structure to represent threads. So the only difference between thread and process is just about how many information they are shared between each other. So if they share a lot, then probably that is a thread. So if most of the informations, most of the resource, they have their own one, then that will be process. Okay, so even during the scheduling, there are same things. So that looks the same in Linux. Okay. So creating a thread in Linux, actually there is a function called clone function. So clone is identical to fork. So except the address space, file system resource, file descriptor, and signal handlers, they are shared between each thread. I mean, created by the same process. Okay, so you can see like for the clone, you can customize what kind of information you are going to share. So like virtual memory, file system, files, and then signal. So they are shared between threads. Okay, so when we are talking about thread, actually there is a very important thing, it's called kernel thread. So usually kernel thread, it likes the daemon or like a monitor. So kernel thread will monitor the system kind of utilization usually. So kernel thread runs kernel tasks in the background. So because it is a kernel task, so kernel threads do not have an user address space. Okay, so kernel thread only have their own kernel space, kernel address space. But just like normal process, kernel thread, they are schedulable and preemptible. So they're just scheduler. They can be scheduled just like the normal process, and also they can be preempted by other kernel threads, for example. Okay. And the thing is, kernel thread different from the user thread is it operates only in the kernel space. So kernel space means CPU needs to switch to the kernel mode to execute it. So when the CPU is in the user mode, CPU cannot run the kernel thread. So actually, because it doesn't have their own user address space, so when kernel thread is going to do the context switch to another kernel thread, you'll be faster, okay, because it doesn't have their own user address part, okay. So this is about process and thread, okay. So after talking about a lot about the process, the final thing is, so how to terminate a process? I mean, there's one day a process calls the exec function. So the process is going to terminate itself. So termination occurs when the process or C compiler calls the exec. Okay. So there are several things we need to do for this process termination. The first is to set the pf-execting flag. So this is just like the process flag -execting. It is a flag in the text structure. Okay, you can find this flag in the text structure, and if it is set, it means this process is going to be terminated. And there are several things that we need to, the system needs to do. The first thing is to exec the MM. So MM makes the memory management to release the memory address space. So the second is to release the semaphore, because for each process, maybe they will hold a lot of semaphores, and we are going to release those semaphores so all the process will not be blocked. Because when the process is dead, for example, it terminates, and if it doesn't release their semaphore, then maybe it becomes a deadlock there. So the other process cannot use the resource. So the third one is a file. And file is quite special here. Actually, it only decrement the usage count of object related to the file descriptor. So because there's some cases is the file will be shared between a lot of process. So we only decrement the usage count. So if one day usage count becomes 0, then we will remove the link here, okay? So the next thing is it execute, they will call it exec notify to send a signal to the text parents to reparent any of the text children to another thread in their thread group or the initial process. Okay, so if the process is going to terminate, and if there are still several children here, then Linux will do the reparent. I mean, we will get the elder kind of process and then to do the reparent. So if there is no elder process, probably we will reparent to the initial process here. So they just kind of the routine things that it needs to do. And then the last one is to do the schedule. So to switch to a new process because the process now is terminated. So the next step is to schedule to run another process. So after the parent retrieves the information, the process kernel stack will be deallocated. Okay, so the kernel stacks, inside the kernel stack, there's several things like thread info and text structure, those kind of things, they're all in the kernel stack, and they will be deallocated. So it means after this step, the process is not alive, okay? Okay, so next thing, we are going to talk about the scheduling thing. Okay, So first of all, let's have a few kind of naming things. So first of all, if we have a single processor, so single processor here, you can think about just like the single core. Okay, so usually people use time sharing to share the single core, like because there's one core only. So if there are several processes they're running, then they need to share this like single core. The reason I didn't say single processor is just like a single CPU is current CPU has a lot of cores. So this is the reason I said single core. Okay, so for a single core, just like if we are going to share this core, for example, for each process, they can get, for example, 1 second to run this core, to use this core. And people are usually calling this is called virtual parallelism. So it's just about each process thinks they are running in a parallel way, right? But actually, they are not really running in a parallel way. They're just using the same CPU. Okay, so you can think about the reason is when the first process is running on is first using the CPU core, then the rest of them they are in a sleep mode. So when the process in a sleep mode, they will feel like they are not running. Okay, so when it switches to the second process, then the first process will again becomes to the sleep mode. So the first process will feel like, hey, it always run when it is awake. Okay. So there is another thing is called multiple processors. So just like there are several cores there. So for multiple processors, it is a true parallelism. So at the same time, it is possible to run, for example, 2 process or like more process. Okay, so the criteria for schedulers, actually there are several criteria here. Just like you want to make your scheduler become so fair, or like you want to have more interactiveness, just like you want to make it have smaller response time to faster response time, or like you are going to have a higher throughput. For example, you can serve for a lot of more process here. So there are different kind of criteria, and each scheduler, when they are going to design their own policy, they will make the trade-off between all these kind of criteria. So there is one category of the scheduler called cooperative. So cooperative scheduler means process will voluntarily yield the CPU. It means like each process they will yield their CPU in a volunteer way. Okay, but this is not what Linux is using. I'm just to let you know there is one category of the scheduler like this. So in most cases, in Linux, we're using a preemptive one. Okay, so preemptive means even a process doesn't want to yield, doesn't want to release the CPU, but there is a way to stop the process, to switch to another process. So you can see there is a word called involuntarily suspend. Okay, so it just means like there is a way for other processes to preempt the other process. So this is what Linux based on now. So here's just a quick example. So when a process is scheduled and running, it is in this time slot, and then if there is a preemption and it is here, so between the preemption and the process starts to run, we call it time slice. So time slice is the time a process runs before it is preempted. Okay, so we have this time slice because we don't want to, because we want to prevent some process monopolizing processors. It means we don't want some process to occupy the processor for too much of time. We want them to become, each process have a chance to run, to use this CPU, okay? So for the scheduler, actually there are several criteria here, just like how to decide a time slice and which process should be run next. Okay, so let's take a pen and then coming back, we'll introduce those kind of things.